Okay, so for exponential growth and decay, what we're doing is we're doing the rate of change raised by the amount of time, or the amount of times, plural. I did that on purpose. It wasn't a righto. Or the amount of half-lives, and we're going to multiply that by the original. So that might not make much sense to you, but this a sub 0, I should say, means the original amount, and this is the final amount. And this is 1 plus or minus the rate raised to the time power. That's kind of the generic equation, but let's go ahead and look at some example problems that might help you understand. We're looking at half-lives, and half-lives are how long it takes for you to have half of what's left. For example, after one half-life, if you start with 80 grams, then after a half-life, you're going to have 40 grams. So the half-life here is 5 years. How much is left after 15 years? Okay, so 3 half-lives have taken place. And that's pretty easy to figure out intuitively. You can go over here, and after you start out with 80 grams, and after one half-life, you've got 40. After 2 half-lives, you've got 20. After 3 half-lives, you've got 10. So the answer is going to be 10. Let me double check that. I did 3, right? Yes. Okay. So I'm going to show you the long way. So hang in there. So we start out with 80, and we have 1 half. Well, we've got 1 minus 1 half, and we're going to wind up with 1 half. And that's raised to, how many half-lives do we have? Well, we have 3 half-lives. Okay. So we've got 80 times 1 half to the third, and we've got 80 times 1 over 8, and we wind up with 10. Let's try it out. And apparently that's wonderful. Okay, this one's going to have, I think, exponential growth. Yes, it doubles every 85 hours. This is our current population of 500 bacteria. What would the population be 540 hours from now? So what we're going to do is we're going to set it up. So we start out with 500 bacteria. So we're going to put, it's getting a little messy, so let's come here. Let me erase this really fast. So we started with 500 bacteria. That's our original population, 500, and it doubles. So in other words, it increases by 100%. So we can use this again. It increases by 100%. 100% as a decimal is 1. And we are going to figure out how many times it doubles. So after 340 hours, it doubles every 85 hours. So we're going to do to the 340 divided by 85 power over 85 power. And we're going to get the answer, we're going to get A of F. Okay. In other words, we're going to do 2 to the 340 divided by 85 power, which is equal to 4. So I'm going to strike this, I'm going to write 4 here. Okay, so 2 to the 4th power is 16, so our answer is going to be 500 times 16, which is 8,000. Sorry, let's look at this instead. It's 8,000, so let's come over here to IXL, and let's type it. Let's see if we get it right, and apparently that's fantastic. Let's do one more. So Robert is an exterminator, visits to control, and I'm going to, as soon as you hear extermination, you're going to know you're going to be working with a minus. So the population has declined 15% every year. If you've got 3,100 cockroaches, how many will there be after 8 years? So 0.85 is going to be our decimal, because we're doing 1 minus 15, and we get 0.85. And how many are there going to be after 8 years? So 8 is going to be our exponent. And how many cockroaches are we dealing with here? We are dealing with 3,100 cockroaches. 3,100. And try to figure that one out on your own. Super. Okay, now we're talking about compounded interest. I'm just going to go ahead and solve this one and do a more difficult one. Actually, I'm done. This is Mr. Jolly signing off.